Thermodynamic properties. The word property has a very specific meaning in thermodynamics, and we will discuss what that is. There are different types of properties, and we will also discuss what those are. A property of a system is any attribute that can be measured without knowing the history of the system. Examples of this would be mass, volume, temperature, energy. Suppose there's a box which is sitting on the floor and somebody slides that to a new position. Now you walk into the room and you asked, what is the position of the box? That is not a very difficult question to answer. You can define a coordinate system, and then using the coordinate system, you can measure the position. You did not need to know the history of the system to measure the position. Position, therefore, is a property of the system. Now, suppose you are asked a different question, which is, how much work was done in moving the box? If you knew that the force F had been applied to the box, and the force had moved it from its position x1 to the final position x2, then you could do a calculation, and you could say that the work W12 is equal to the force times the displacement, which is x2 minus x1. But in this case, you needed to know the history of the system to calculate the work done. So therefore, work is not a property of the system. It is a transfer of energy from the surroundings to the system. Let's talk about notation that will help us differentiate between properties and other quantities that are not properties. So suppose the box is sitting on the floor and you move it by an infinitesimal amount, dx. The total displacement is delta x, which is x2 minus x1. Now, if you wanted to calculate the displacement delta x, you could do that by integrating dx from its initial position x1 to its final position x2. But how much work is done in moving through an infinitesimal distance dx? It would be an infinitesimal amount, but how do we denote an infinitesimal amount of work, w? Should it be dw? If it is, in that case, by analogy to our earlier statement that delta x is the integral x1 to x2 of dx, we should be able to say that the work is the integral of dw from w1 to w2. But w2 and w1 are meaningless terms. w1 would mean the work at position x1, and that doesn't mean anything. So therefore, an infinitesimal amount of work will be denoted by delta w, not dw. And this will remind us that work is not a property, and therefore it cannot be integrated in the same way that we integrate properties. Now, the correct way would be saying that when a force F moves an object through distance dx, the work done, delta w, is F times dx. And therefore, w12 would be the integral of f dx, but the limits of integration over here would be x1 and x2. Suppose we are heating up a beaker of water. Now you walk in and you ask, what is the temperature of the water? That's easy enough to do. You can put a thermometer into the water and you can measure the temperature. Temperature, therefore, is a property of the system. But suppose you are asked how much heat has been added to the water. If you knew what the initial temperature was and what the final temperature was, and if you knew the mass of water inside, you could actually calculate this. But this means that you need to know the history of the system. Heat is not a property. It is a transfer of energy to the system. And therefore, we are going to denote an infinitesimal amount of heat added to the system by delta Q, not dQ. We have over here a bucket of water which is sitting under a tap. A drop of water falls out of the tap into the bucket, but the bucket has a leak in it, so another drop falls out of it. If we wanted to analyze this system and do a mass balance, we have to remember that m, the mass of the system, is a property. We can always measure the mass of the system. Therefore, the change in mass will be denoted by dm. But if we are talking about the mass being transferred to or from the system, that is not a property of the system. So we will denote that by delta m. So the drop falling in is delta m in, the drop falling out is delta m out. Now we can get a relationship between these terms. So the change in mass, dm, would be the difference, delta m in minus delta m out. We've got a table of height h, and there's a box sitting next to it. Now, we pick up the box and we keep it on top. If we want to calculate what the change in potential energy is, delta PE, that would simply be mgh. Now, instead of just picking up the box, suppose we make it easier and we get a ramp. And then we slide that box up the ramp until it's sitting up on the table. Now, if we want to calculate what the change in potential energy is, it's going to be exactly the same, mgh. So potential energy is what we call a point function. The value depends only on the state of the system. It doesn't matter how the system gets from one state to another. So all properties are point functions. Examples of this would be mass, temperature, energy. On the other hand, you have what is known as a path function. And a path function is one in which the value depends on the start and the end state of the system and the path followed to get from one state to the other. Examples would be work or heat. Now, there are different types of properties. Suppose we got a piece of metal and we know the mass m, the volume v, the temperature T, and the density ρ. Now we take a saw and we cut this and we make two equal blocks. So the mass of each would be m by 2, the volume would be v by 2, but the temperature T and the density ρ are the same for both blocks. So obviously there are different types of properties. So an intensive property is one which can be specified at a point within the system, and it is independent of the system mass. So examples would be temperature or pressure. On the other hand, an extensive property is one that depends on the mass of the system. Examples would be mass, volume, or energy. For any extensive property, we can define a corresponding intensive property. If we take any extensive property and we divide it by the mass of the system, that gives us a new intensive property. As an example, if capital V is the volume of the system and we divide it by the mass, it gives us a new property which we call the specific volume. This is an intensive property and it has units of meter cubed per kg. Similarly, if we take the energy of the system, which is denoted by a capital E, and divided by the mass, that gives us an intensive property, which is the specific energy. In general, uppercase letters will be used to denote extensive properties, and lowercase letters will be used to denote the corresponding intensive properties. To summarize, a property of a system is any attribute that can be measured without knowing the history of the system. Properties depend only on the state of the system, not the path followed to get to the particular state. An infinitesimal change in a property x will be denoted by dx. On the other hand, if y is not a property, an infinitesimal change is denoted by delta y, not dy. Intensive properties are independent of the system mass, whereas extensive properties depend on the mass of the system.